Okay guys, so today we're going to be doing Leetcode 2090 K-radius subarray averages. So the prompt says, you are given a zero-indexed array nums of n integers and an integer k. The K-radius average for a subarray of nums centered at some index I with a radius k is the average of all elements in nums between the indices I minus k and I plus k inclusive. If there are less than k elements before or after the index I, then the k-radius average is -1. Build and return an array of averages of length n, where averages I is the k-radius average for the subarray centered at index I. The average of x elements is the sum of the x elements divided by x. Using integer division, the integer division truncates down towards 0, which means losing its fractional part. So okay, so we have an example input right there. We have 7, 4, 3, 9, 1, 8, 5, 2, 6, and we have our k as equal to 3. And as you can see, that's the correct output, or the desired output. So let's brainstorm ways we can do this in a naive way, or in a the most inefficient way possible. So the most inefficient way possible would be if we have a value k, and we know that we have to be able to make a value such that we have to be able to add values such that we're at an index such that there's k to the left and k numbers to the right. Well, we already know we have to start off from 0 to 3, the third index, and the brute force way that we'd go about doing this is we would go to this first index, and what we do is we just simply add all the numbers to the left and all the numbers to the right up to the kth number. So for 9 we'll do so let's actually write this output array. So for the first index we'll have -1 because we don't have k numbers to the left of it. Same thing with the the 1th index, the index 1. Same thing for index 2, and for index 3, or the element 9, we do have k numbers to the left and k numbers to the right. So the brute force way would be we'd simply just add all k numbers to the left and all k numbers to the right. So what are the k numbers to the left? We have 7, 4, and 3. And remember, our k is 3, so we only add 7, 4, and 3. And obviously, we don't have any numbers beyond this 7, 4, and 3. So 7 plus 4, 11, 11 plus 3, 14. And then what are k numbers to our right? 1, 8, 5. So we have 9 plus 5, 14. So we have 14 here, and we have 14 here. And 14 plus 14, 28. 28 plus 29, we get 37. So once we get 37, we just take the radius, or the number of numbers of the diameter of our window, or essentially the number of numbers we've added. So how many numbers have we added? 3 here, 3 here, 3 here, and then we have 1 here. So that's 7 numbers. So 14 plus 14, 28, 28 plus 9, 37, 37 divided by 7. Remember, we have to truncate down, so essentially we have to do 37 divide the double division sign, 7, and we just get 5. Keep moving forward. Let's repeat that with 1. With 1, 9 plus 3 plus 4, 12 plus 4 is 16, and then we have 16 on the left. Now 8 plus 5, 13, 13 plus 2, 15. We have 16 on the wait, 3 plus 4. We have 16 on the left, and we have 17 on the we have 15 on the right. So 16 plus 15, 21. 21 plus 1 is 22. 22 divided, again, we're adding 7 numbers. 22 divided by 7 is simply just 3. Oh, okay, I see I did my math wrong. 4, 3, 9, my bad. 4, 3, 9. 7, 7 plus 9 is 16. 16 plus 1 is 17. 17 plus 8 is 25. 25 plus 5 is 30. Uh, yeah. And then 30 plus 2 is 32. Okay, so I did my math wrong. 8 plus 5 is 13, 15. So it would be 31 plus 1, 32. 32 divided by 7 is 4. So here, 32. And then we keep moving forward. Again, we have, our center number is 8. Add 3 numbers to the left, 3 numbers to the right. We have 3 plus 9, 12. 12 plus 1 is 13. 13 plus 8 is 21. 8, 21 plus 5 is 26. 26 plus 2 is 28. 28 plus 6 is 34. 34 divided by 7. Again, so that's 4. So this would be 5, 4, and 4. And then for the last two numbers, the numbers centered at 2, we have k numbers, at least k numbers, or we have k numbers to our left, but we don't have k numbers to our right, so this is negative 1. And then same thing for 6. We have k numbers to our left, but we don't have k numbers to our right, so this is negative 1. So this is our final answer. Negative 1, 5, 4, 4, negative 1, negative 1. And as you can see, it matches the output as well. Now the issue with this approach is that, well, if you look, what is the work that we're constantly computing over and over again? And actually, let me state the time complexity of this approach. The time complexity of such approach would be O of n squared space. I mean O of n squared time and O of 1 space. Reason being, O of n squared time is because, not O of n squared time, my bad. That's if we're assuming k is at most n. But for accuracy purposes, let's say O of n times k. Because, why is it O of n times k? Well, for each, let's just say for each number, we're going to be, at worst case, we're going to be doing a k iteration from on the left and on the right to get our sums. So that's why it's O of n times k. And actually, let's simplify this back to O of n squared, because essentially the problem's constraints do say that k can be up to the size of n. So yeah, the problem constraints say that k can be at most n, so it's possible that this problem is at most O of n squared. So yeah. And the space is just O of 1 because we're just doing simple additions and we're not using any external data structure to keep that addition, to like do that addition or any sort. So yeah, that's why it's O of 1 space. So yeah, this algorithm is completely fine and works, but the issue is it's you can simplify on it. And if you look, there is a certain work that we're constantly repeating that doesn't need to be repeated, and we're always repeating this work to get the sum of our left and right side. And what might this work be, if you're wondering? So, let's say we have a number. Let's say we have 2, 3, 4, 7, 1, 2, 3, with k equal to 2. Well, we know that for a fact this won't have an answer. We know that this won't have an answer. We know that This will have an answer, so we'll leave that blank. This will have an answer. This will have an answer. Uh, so, and then these two numbers will not. So, if you look, every single time we're computing the sum on the left and on the right for the number that we're centered at currently. So for 4, we add 2 plus 3, and then for the left and on the right we add 7 plus 1, and then we eventually add 4. So if you look, there is, when we're moving on to the next, so once we add 2 plus 3, once we add for 4, once we do 2 plus 3 plus 4 plus 7 plus 1, there, so we add this, we get our answer. So let's just say this answer is n1. Well, once we get this sum, there's no reason to, when we go to 7, this part of the sum will be used, and some of this part of the sum, but this won't. Essentially, this part of the sum will not be used. So, if you look, there is no reason why we should be recomputing the sum of 3 and something like 3 and 4, and the sum of 1 and the sum of 1 plus 1 and 7. Because again, yeah, 1, we could also say that 7 will not be reconsidered when it's being centered, recentered, when it's being centered. So we don't really need to recompute sums such as 3, 4, the sum of 3 plus 4 plus 7 plus 1. All we really have to do is just drop this 2 and then welcome the incoming number into our window. Now, if you recognize, I used the word window, and this might give a clue as to what the solution of this answer is, or the optimal solution. So all we have to do is just drop the number at the end and include the number in the beginning into the sum. And instead of recomputing the sum of all these numbers, 3 plus 4 plus 7 plus 1, by iterating through the left and the right? So essentially, this problem just boils down to sliding window. And the way you would do this is once you get to a point where your window, you can make a window of the given size based on your k, you can then, all you have to do is every single time you're centered at a number, just before you move on to the next number, all you have to do is just subtract the number at the end of your window and then add the number, the new number into your window. Now, how do we go about doing this? So let's actually run through this example. So 2, 3, 4, 7, 1, 2, 3. So I'm going to put the answers right here. So remember, we know that this is -1, -1. This is an answer, this has an answer, this has an answer, -1, -1. So first, 2, 3, and the window size we're going to be looking for is, write this out, 2 times k plus 1. Why 2 times k plus 1? Well, 2 times k because k, we have k numbers on the left and k numbers on the right, and then plus 1 because remember we have to also add in that number at the center. So if we have a k of 2, you'll recognize that a window size of the numbers that we're adding will be 2 times k plus 1, which is just 5. So yeah, 3, if we're, let's say, centered at 7, if we're centered at 7, our window size will be 3 plus 4 plus 7 plus 1 plus 2. But yeah, let's go back to the example. Let's start at 4. So if currently our window has, let's say our window sum has a sum of 5, has a sum of 5, has a sum of 5, uh, and then we've got we've gotten to this 4, and the reason why it has the sum 5 is because we added 2 and 3, and we don't really do anything there because, you know, there's no numbers, there's not enough numbers to its left and not enough numbers to its right. But yeah, we keep moving, we get 4, we just add 4, we don't do anything with it now. We add 4, okay, we get 9. So then we get 9 when sum is 9. And then we add we add 7. So currently our window size is this. We add 7. We get when sum is 16. And then we add 1. So we get when sum is 17. So now our window size is this. And we now know that our window is of size 2 2 times k plus 1. We know our window size is of size 5. This is where we stop and we calculate our average. And we also know where our center is going to be is because all we got to do is when we're processing this 1 or this number at this index, all we know that the number when we're processing the average, when we know that our window size is of this size, 2 times k plus 1, and the number we just processed is going to be at the edge of the diameter of the window. Or essentially it's going to be take the index of the number, it's going to be I minus k. That's I minus k. I minus k is gonna give us the index of our center. So in this case, our k is 2, and we want to find the average for the center 0, 1, index 2, element 4. So in this case, we see that our window size is 2 times k plus 1. It's 5. And our index right here is 0, 1, 2, 3, 4. It's 4. 4 minus 2. We know that our center is 2. So we go to 2 in our result array, index 2 in our result array, and we put 17 integer divide by 5. Okay, now that that's done, we keep moving forward. We add a new number to our window. But before we add a new number to our window, what we should do is subtract. So previously our number, we had 2, 2, 3, 4, 7, and 1, right? Now we're going to add the number 2, this 2 right here, to our window. But if we do that, our window size is going to be bigger than it should. So what we have to do is drop the number at the end. So we're going to drop the number at the end by subtracting it from our win sum. So we're going to subtract 2, and now our win sum is going to be 15. But we add back the 2 because we're adding in a new number. So 15 plus 2, 17. Our win sum is 17. So now our win sum incorporates this, and now we just do again the reason why we know the center of our radius, or the center of our diameter, is because the current index we've just processed is at the very edge. So all we have to do is just take that index. So this is I believe this is 5, and we just do 5 minus the radius, which is 2. 5 minus 2. We know that our answer is gonna be this is the answer for index 3. So all we just do is 17 divided by 5. And then repeat the process. We drop the number at the end, 17 minus 3. Now we have win sum 14. And then once we drop that, we add a number. We add a number at the front. So now we have these two. we have these two. We added this number 3. So again, we dropped. We have dropped the 3, and we just add the from the back, and now we add the 3 at the front. So again, win sum is 17. And again, the reason we know that our answer goes to index 4 because this is index 6 and our radius is 2. So 6 minus 2 is 4. We just put 17 divided by 5 right here. So this would be 3, 3, 3, and that is our desired output. -1, -1, 3, 3, 3, -1, -1. So yeah. So one might wonder what the time complexity of such an algorithm is. Well, the time complexity of this algorithm is O of n, and our space is O of 1. Now, the reason why it's O of n is because all we're ever doing is we're going over each element at most twice. So that's 2n. Drop the 2 because we're doing asymptotic analysis. So it's at most O of n. That's just a simplified way or the fast way to think about it. If you look in our sliding window, we only ever go over every number in terms of like adding or subtracting from the window. We only go over every number at most twice. And this is demonstrated when we're adding these first two numbers, 2, this 2, 3. So we added them to our window, but then also we subtract them once they get out of the window. And then our space is just O of 1 because we're not really using any external data structure or any sort of variable size list in comparison to the input to keep our answer or our sum. All we're just using is a regular integer variable to keep our sum, our rolling sum or our window sum as we're going through the array. So yeah, let's now go to the coding section. So yeah, first let's make a result array because we need to keep our answer somewhere. Just gonna make this the size of nums, and then we're going to have a variable to keep track of an integer variable to keep track of our window sum. We're gonna name this current sum, and then we're going to have a variable to essentially keep track of the last element within our window, or essentially the back of the window, and this we're gonna call this start. So just gonna do for and in range length nums. So we're going to, when we're processing each element within the nums array, we're going to be adding it to the current sum. And then afterwards, after we've added it, we're going to check if the size of our current window is big enough so we can start computing averages. So we're going to check if I minus start plus 1 is equal to 2 times k plus 1. If it is, then we're going to do result, and our result, our answer or our average will be for the index that is located at I minus k, or not I minus k, my bad, end minus k. This should be end minus k, because that is where our the center of our diameter will be. Now the average will just be the current sum, integer division by 2 times k plus 1. And then now that we have our window, before we have our window, we don't want our window to overextend when it goes to the next iteration. So we have to drop the last number, if you remember. We have to drop the last number. How do we drop the last number? We just subtract it out. So we do current sum minus nums start. And then once we do that, we have to move up our pointer to the next number. Start plus 1. And then at the end, just return result. And yeah, that is the code. Let's run it. This is good. And yeah. If anyone has any questions or comments or concerns, please let me know in the comment section. Yeah, till next time.